I'm going to attempt in this video and probably another one or two to try to explain why Lagrange multipliers work. It's really hard to conceptualize why setting up this equation, if I've got f as my objective function, I'm trying to minimize or maximize f, and then I have g as a constraint, why this equation works with this lambda. So I'm going to try and pull from various things that we've learned about multivariable functions and put it all together and make sense of why Lagrange multipliers work. So the first thing that we're going to look at is parallel vectors. And this should be really familiar, but I just want to make sure everyone's on the same page. Say I had a vector that started here and ended here. It went like that. And this was vector A. You should see that that's clearly 1, 2. And say I had a vector that went from here to here. And this was vector B. You can see that these guys are parallel. I can grab this vector and move it around, and it's still that same vector. So you can quantify this by saying A is 2 times A is equal to B, right? So if I double this vector A and I were to lay it over top of B, that would be the same, right? So the key about parallel vectors is that they are constant multiples of each other. So if I took negative 3A, that would be parallel to A. So I can do any constant multiple of a vector out front of it as a scalar, and that new resulting vector will be parallel. So that's important. And the next thing that we're going to talk about is contour graphs. So let me pull up a couple contour graphs. So here I've got f of x comma y equals x squared plus 2y squared. It's a paraboloid. You should be able to visualize what it looks like. If I were to do a 3D graph of it, it would look like this, right? And then if I do a contour plot, which is represented as the same thing, it looks like this. These contours are separated by 0.2s, right? So this graph, this spot right here is f equal to 0.2. This is f equal to 0.4, and so on. What they are representative of is, this is 4, 6, this would be f equal to 1 right here. If I were to go and draw a circle around here, right, then that contour, that line right there would be the height of 1 on that surface, right? That would be this circle right here. This circle right here, this f equals 1. And I could go and draw the next one, and the next one, and the next one, and all of those would be just drawn on this 2D XY space, right? So you can see that it's tighter this way than it is that way. That's this x being tighter than that y. Next thing that I want to talk about is how the gradient, the del of a function, relates to its contour plot. So del f is equal to f sub x comma f sub y, partial f, partial y. So it is true that if I take del f at any given point, it will be perpendicular to the contour plot. So say I take it here, it'll be perpendicular to that contour plot. Say I take it at this spot right here, it'll be perpendicular. Wherever I take del f, if I place it, because remember, del f is a vector, right? So it would look like that. If I were to start it at that x comma y where I evaluate it, and then place it over top of the contour plot, it will always be perpendicular. And I'm going to prove that to you. So what we're going to start with is what actually are these contour plots? Remember, this was f equal to 1, right? And this was f equal to 0.2. So those contour lines are actually just when I take this f of xy and I set it equal to a constant, right? So for example, this one right here is x squared plus 2y squared equals 1. That would be this contour plot right around there, whatever the one that's f equals 1. If I were to do x squared plus 2y squared equals 1.2. Since I've plotted this with gaps in the contour of 0.2, that would be the next one out. So I want you to see that f of x comma y is equal to a constant gives me that those different contour lines. Now what I want you to see is that I highlighted that one in red. That would be this equation right here. Now, that's not the only way that I can represent that ellipse. I can also parameterize it, right? I can write it with a parametric equation. In this case, that would be x, go back to blue, x equals cosine t, and then y equals root 2 over 2 sine t. Don't worry about where that comes from so much, but just that I could write that as with that parameterization. If I take it from t equals 0 to 2 pi, it would start here, and it would go around like that. So, bottom line, when I get my contours, I can actually write them using a parametric equation in the xy plane. So, what that means is that this f of x comma y equal to c could really be thought of as f of x of t comma y of t is equal to a constant, right? So in this case, it would be this equation where this is the x of t, this is the y of t, and the c value is 1. That gives me this curve right here. So now what I want to do is show you how that relates to this del f. So I'm going to go in a general form right here. So if I had f of x of t comma y of t equals a constant, arbitrary, that could be any contour line, any contour curve, any level curve. What I can do is derive that with respect to time. Now, this uses chain rule, but it's not the complicated one. It's a simple one. What do I get when I do this? Well, I get I'll write it in the easy way, f sub x times dx dt plus f sub y times dy dt. That would be the derivative of the left side with respect to time, is equal to, well, if I've got a constant on the right side, it doesn't change as time changes, so I get 0. Now, what does this give me? Notice I could rewrite this using vectors. This is f sub x, comma, f sub y, dotted with dx dt, comma, dy dt. So, what is that? Well, notice this is del f, and this is x prime of t, comma, y prime of t. And look, their dot product is 0. What happens when I have a dot product equal to 0? Well, the two things are perpendicular. So del f is perpendicular to this. So then the question is, what is this? Well, if I have some general contour level curve like this, right? If I'm out at this spot, the prime, this guy right here, is parallel to the motion of the curve. So this would be x prime of t, comma, y prime of t. It would be tangent, right? And then del f, well, it's got to be perpendicular to that piece, right? So what's that mean? It comes out like this, right? So that is perpendicular like that. But as I move this piece around, this prime vector is going to maintain its tangent nature. And since del f is perpendicular to that thing, then del f will always be perpendicular to the level curve. So hopefully that makes sense why, if I draw a level curve like any of these, and if I were to plot del f at it, it would be perpendicular. It's because of the chain rule with a little bit of parameterization and the fact that if two vectors dot product to 0, they're always going to be perpendicular. Okay, so I should have said in the beginning that I'm going under the assumption that you've done at least a handful of Lagrange multiplier problems, but you don't understand why it works. So I'm going to pull in an example now. I'm using that f of xy from above because I want to talk a little bit about the constraint and how the constraint actually has this same property that I talked about up here that the level curves have. So, if I had the example, and I assume that you could do this, minimize and maximize, so find the minimum and maximum values of f of xy, so this paraboloid, subject to the constraint x squared plus y squared equals 1. So that's the unit circle. So my objective function is always my f of x comma y. My constraint is this function, x squared plus y squared equal to a constant. So in this case, my constant is 1. You could always have a constant of 0 too. And I could actually write this one as x squared plus y squared minus 1 equals 0 and treat this guy right here as the constraint. And I would get the exact same results as if I were to treat this as the constraint. So it doesn't really matter where this guy stays because when I do the derivatives, it just goes away. So what I would argue is that everything that I did up here for f of x, y equals a c, I could parameterize it. I could take its derivative. I could get this dot product. I would get it equal to 0 because there's a constant on the right side. Therefore, this would be perpendicular. The entire argument that I posed for this right here is the same as for this piece right here, because this is the same form. It's g of xy equals a constant. So I could do the exact same math that I did up above, and I would get that del g is perpendicular. And now you may say, is perpendicular to what? Well, del g is perpendicular to g of x comma y equals c, right? So whatever this g function is over here, if I were to plot that, I would get that it is perpendicular. If I were to plot it anywhere on this unit circle, the del g would be perpendicular to that unit circle. And that's actually, we can show that really easily, right? Let me just go out to root 2 over 2, root 2 over 2. What's del g? It's 2x comma 2y, right? And what do we know? Well, that's going to point out at a 45-degree angle from the origin, which is going to be perpendicular at that root 2 over 2 spot. So del g is always going to be perpendicular to the constraint. I'm going to stop this video here and pick it up in the next one. So I will see you in the next video.